Well, good morning. A lot of excitement, I guess, about the quiz. Okay, are there any questions before I begin? No? How are you doing on the second assignment? How many are having problems?
Yeah, I don't understand what to do with the second equation. I
Okay, let me try to open up.
feel like while 1 and 2,
Okay, let me just take a minute to clarify any questions you have on assignment 2, and then we move on to the lecture. And I know you guys are excited to get the last answer to your quiz questions resolved. Please quieten down. As for the second assignment, I guess our scheduling of office hours is probably not the best, because I hand you the assignment on a Tuesday, and Tuesday afternoon I have the scheduled office hours. But as I told you, I'm always open. But my schedule, I think, is getting busier. So what I will do is on Saturday morning from 10 to 12, we will try out this remote help. Okay, so there is a virtual classroom in the Moodle. So there is a link in the Moodle. If you go and click onto that, you can enter the virtual classroom. And basically, I'm going to be at my home, but on the virtual classroom. So anybody who logs in can come in and say, okay, I need help on the assignment on this part. The nice thing about that is I can actually see what is happening on your desktop. You need to be working in front of a computer. So if you're working on the assignment during that time, I can try to walk you through that. Okay, if there are problems, I can try to demonstrate how to overcome those problems remotely. Okay, so yeah.
And what time did you say this was on Saturday?
I'm planning 10 to 12. This Saturday, 10 to 12. Is that a good time?
Yeah.
Okay. So I will show you, I guess, on Moodle. Do you guys know where that virtual classroom link is? You can find it out?
Yeah.
Yeah, it is. It's called Adobe Connect Pro. It's a program that allows, it's like Skype. It is like Yahoo Messenger, Instant Messenger, except I think even Skype now allows you to share the desktop. So you could see my desktop, I could see your desktop. So as you're working on your assignment, if you share your desktop, I can see what you're doing, where you're making mistakes, and help you through that. And it doesn't have to be necessarily one-on-one. Many people can come into that virtual room at the same time and observe what is happening. So I'm going to serve on a first-come, first-served basis. Okay, so I'll open up the thing at 10 o'clock. Anybody logs in at 10 having a question, I will answer theirs first, but as other people come in, we'll just queue them and try to take it as far as possible to 12 o'clock. And most likely what you will find is if you're observing somebody else, you'll find your own problems are kind of resolved, so it might help that way. And also we could kind of record that whole session and put it online if you permit my interaction with you on a one-on-one basis. Okay, but there we need the permission of the students to be able to put anything online. I won't put it on YouTube, but you could put it within Moodle so that only this class will have access to it. It's something that you need to think about if you're comfortable sharing that kind of an interaction with other people. It's a good way of spreading the solution and help to other people instead of repeating the same thing for me with everyone. Okay, so we'll give it a try. I am a technology geek, as you can tell, so I do try to explore these newer ways of helping learn. Okay, in the teaching and learning exercise. Now, the question that you have is about the second assignment, right? The second assignment is essentially the generalization of what we saw in the class in using FSOLVE. So every assignment will be like this. I take you through the process of identifying a particular type of problem. In this case, we're talking about a system of nonlinear algebraic equations. Okay, and then FSOLVE is the tool in MATLAB that's going to help us solve that. So we are then showed how to do that with just 3 equations, 3 stages. Now what I want you to do is take the same idea, so you can go back to the lecture and listen to it if you want, and generalize that to n stages, where n could be 10 or 15 or 20 or whatever it is. Okay, so these are the equations, and your question is pertaining to what do you do with this?
The second equation.
The second equation.
Yeah.
Oh, okay. The second equation is actually a set of equations. That's where the generalization actually occurs. The first equation is for the first stage, and I guess I should have opened this. Let me see whether I can write on this one. Okay, the first equation refers to this stage, and in that stage, typically you might have L and X naught as being given. So you have to treat the L. Sorry, maybe L is the one that you're solving in this case. So X naught is given. Okay, so you have to treat that as an unknown. So you need to write that equation as F1 is equal to, okay, V times Y2 minus Y1 minus L times X1 minus X0 equal to 0. So this is not working well. Let me try to open this in the other program. Assignment. Okay. All right. Okay. So specifically in this problem, let me see what is asked. In the first case, you are given yn plus 1 xn x0. These are all given to you. Okay. So yeah, in the first case, L is also given. What is not given? V is not given. Okay, so you need to solve for V, and we need to solve for all the other compositions. So those are given to you. X, the things that you need to solve for are given in this vector, x1 to xn minus 1 and V. Okay, so the first equation you would rearrange as F1 is equal to V times Y2 minus Y1 minus L times X1 minus X0. You want to make that equal to 0, but you're not going to be able to do that. FSOL is going to be able to do that, but you need to write a function for that. In the next set of equations, I actually have many equations. Okay, so what you need to do is you need to, what would you think? You have the option of writing F2 equals, F3 equals, but you don't know when to stop.
Yeah.
So the ideal thing would be to use a loop, a for loop. Okay.
So you would place that after the second one.
After the first statement, after the very first statement would be function.
Yeah.
The second statement would be defining whatever constants that you need to define, the k and stuff like that. Then you will have F1 equals, and then you will have for I equals 2 colon n minus 1. Of course, n should also be defined before. And then you would exactly have that statement, Fi. So here actually it should be F1 within parentheses. So Fi equals exactly the same thing, left hand side minus right hand side. Okay, and then you would end it, and then you will have Fn equals. That would be your last statement. Okay, and that way you can make it general for any number of stages. Okay, so I thought that would be the stumbling block in generalizing from 3 stages to n stages. And the natural thing, you already have the right idea, is to introduce a loop so that you can generalize that. Loops generalize it under various conditions. If you know you need to calculate it under a certain times. If n is 10, you need to do it 10 times. I don't want to write 10 equations. So this loop will help you do that. But if you don't know a priori how many times you have to do that, what kind of loop structure will you use? While. So when a certain condition is met, but you don't know beforehand when that condition will be met, okay, then you would use a while loop. Okay, and the other one is conditional branching. That is the if statement. If certain condition is true, do certain things. Else, if some other condition is true, do something. So these are the 3 programming structures that you need to basically master so that you can solve a variety of problems. Okay, does that help? Are there any other questions on this assignment? Okay, so on Thursday morning between 10 and 12, I'll make myself available online. Okay, don't come to my office, the virtual office. Okay, if there are no questions, let me go to the lecture, which is in the last lecture we saw how to solve ordinary differential equations. Okay, the way I'm introducing these topics is there is a model, we develop the model, we understand the nature of the model. Then we pick the tool and we illustrate how to use the tool. Okay, in the second half of the course, we'll be looking at how does MATLAB actually solve these kind of problems. What are the algorithms? Okay, but right now, if you at least get this part in this course, this would be the minimum threshold that I will set for you to pass the course, would be to identify the model and use MATLAB to solve the model. Then as a process engineer, you're well equipped with process modeling techniques. So in the last lecture, we saw ODE-IVP. Okay, ODE-IVP is one function that is good for certain classes of ordinary differential equations. These are initial value problems, okay, that we are solving. Today I'm going to illustrate something called ODE-IVS, and we will see qualitatively what are the differences between those and why do we choose one versus the other. Okay, but in the last class we saw a lot of MATLAB related abilities, that is how to write scripts in cells. Okay, we saw the concept of a cell. And then we saw how to do parametric studies, changing the parameter over a range of values, and how to generate a report which might be useful. You may want to try in doing the second assignment. And then passing the global variables, etc. And the automatic plotting option in ODE using options. There we talked about structures of variables. Okay, and then the finally most important thing is how to do time varying control. Okay, so if I want to maintain an ambient temperature for a certain time and then change it in a programmed way, how do we pass that information from the main program to the integrator? So all these features are important things for you to remember from the last lecture. But the last lecture was about solving a system of linear ordinary differential equations. Now we are going to go into nonlinear ordinary differential equations. It's called the Van der Pol oscillator. We have two equations in two unknowns. Y1 and Y2 are the unknowns. Once you see that equation, immediately you should be able to understand and decipher the modeling features of it. Time is the independent variable. Y1 and Y2 are the dependent variables. And in the dependent variable, you have nonlinearity. So these are nonlinear differential equations, ordinary differential equations. What else do we know? We know that it is an initial value problem. What do you understand by an initial value problem? It's a problem where all the conditions for Y1 and Y2, the dependent variable, are given at one initial location, that is t equal to 0. Later on, we will see something called boundary value problems, also ordinary differential equations. Okay, these are ordinary differential equations of the initial value type because they're all given. The initial condition is given at t equal to 0. So in this case, the first variable is 2. The second value of the variable y2 is 0. Okay, so our task is to solve this differential equation and look at the solution profile and see what would happen. Let me ask you, if I give you this equation and say, go and find me a steady state solution for this, what will you do? These two equations, I give it to you in an exam and say, go and, what approach would you use to find the steady state solution? You would set, at steady state, what do you know? Things don't change with time, right? So you would set this equal to 0, this equal to 0. That means you will set f1 equal to 0 and you will set f2 equal to 0 at steady state. So what do you have then? You have system of two nonlinear algebraic equations. What tool would you use in MATLAB to solve that? fsolve. Okay. If you make that connection, then you know how to write those two functions to pass on to fsolve. You can look at the template that we had on how fsolve is set up, and you can solve the problem. Okay. So the steady state often is a subset of the full dynamic problem. So in the full dynamic problem, we want to generate y1 as a function of time, and you might find that it reaches a steady state like this. In this particular problem, we are going to see something different, something unique. Okay, so there is no steady state. If there is no steady state, what would fsolve do? It will never work. Okay, so that may be part of the next assignment where I will ask you to use fsolve to find the steady state, and you should know when fsolve doesn't work, why doesn't it work? Is it because there is no steady state solution for that problem, which can happen, or is it because you have a poor initial guess? Okay, so that it doesn't converge. Okay, so those concepts of how, when it doesn't work, what do we do, is something that we need to dig a little deeper later in the course when you look at how does fsolve work, how does ODE-IVP work, etc. So right now we are just going to set up the function to write these. And let me ask you this question. If I say this is a problem, go ahead and write those two functions. How many of you can do that? Feel confident that you can do that? No? Okay, it's not very difficult. I have the function here, but let's just close that and just start MATLAB. And let's write that function from scratch. Okay, so edit vpol.m, maybe vpol test.m. You can give any name you want, okay, to the function that you're going to write. This is what you would do. It says file does not exist. Do you want to create it? Of course I want to create it. Okay, now remember I need to switch between these two functions that I need to see. Okay, so let me just I need to see this function, switch between these two. Okay, so I'm going to kind of position it so that I can access both. So what would I start? I would start with, I'm writing a function, so the first keyword is I would start with function space. I want to give the function a name. Okay, that is the variable into which the function will be returned. So f equals vpol, and what should the next parameters be? These functions could be functions of time and functions of the unknowns y1 and y2. Okay, so for ODE class of functions, the input argument is always t comma y. Okay, the first set refers to the independent variable time. The second set refers to the dependent variable y. And the length of y, the vector, how many elements are there in y, depends on the problem. If I give you 4 ordinary differential equations, the length of vector y will be 4. If I give you 2 ordinary differential equations, the length of vector will be 2. So this function will automatically know that. When you're calling this, you're going to send 2 values or 4 values, etc. Okay, so that's the input, that's the output, that's the basic structure of the function. Any questions on that? You have to go through a very similar exercise in setting up your second assignment too. Okay, writing a function from the scratch, given the functions that are in front of you, how do we program it? Now, this function doesn't have as many parameters. If you can look at it, the first one is simply f1 equals y2. There are no constants, there is nothing there. Okay, so you can just go ahead and put a comment if you want, van der Pol equation. Okay, and then put f1 equals y2, semicolon. That's your first equation. The first equation is extremely simple. F1 is simply y2. Okay, you could have a more complicated expression on the right hand side, but you have to program that. That's not very difficult. Okay, well, you cannot do things like, for example, f1 equal to y2. Common mistakes students would make. Okay, what is the difference between f1 and f parenthesis 1? F1 is a variable name. It could be a scalar, it could be a vector, it could also be an array. Okay, but f1 refers to a variable, whereas f refers to a variable. And if you put f1, that says it is the first element of an array f. Okay, any questions? If you have questions, please do stop and ask me. Okay, the second line will be the second equation. F2 equals, you need to look at that, 1000 times 1 minus y1 square times y2. Okay, 1000 times 1 minus y1 square times oops, times y2. I'm just going to go back and forth. Okay, if I make an error, please correct me. Okay, 1000 times 1 minus y1 squared times y2 minus y1 minus y1 and that. Okay, and then make sure that the parentheses are matched. 1 minus y1 squared times y2. That's all you need to do. And save this function. Okay, the function name we have given as vpol test. Okay, any questions on that? So it's really not difficult. Now the difficulty would be, here I have only 2 equations. I always take the simple ones because I don't want to spend writing 10 equations. But in an assignment you have the time. So you can write the 10 equations or 100 equations using loop structures and stuff like that. Conceptually, that's all it is. You know how many equations there are, and you need to write a function that will calculate. The next step would be testing whether this function actually works or there are any problems. Okay. Now here it tells, when it is highlighted with that, there is it thinks there is a problem. So you might want to ask what the problem is. It thinks input argument t might be unused. It is true, because I don't have t appearing either in F1 or F2. I could have it, but in this case I don't have it. So it thinks it's an error, but it is really not an error for this problem. Second one, when I take it near vpol, this is a very common problem that students make. Okay, it says function name vpol is known to MATLAB by its file name vpol underscore test. Okay, so the function name that I give here is not the one that MATLAB is going to know. MATLAB is going to know this function by the file name in which you have stored it. Okay, the file name is vpol underscore test. That's what I gave it. Okay, and I'm okay with that. I can live with that, because when I call ODE-IVP, I need to specify vpol underscore test, not just vpol. Vpol is just a function name that I use inside this. Okay, later on we will see that you can have many functions in a file. These are called sub functions, and their visibility to MATLAB is limited only by the file name. Okay, now I have saved that, and how would I use it? I can type it first to see that it exists. It is known to MATLAB. What do I mean by saying it is known to MATLAB? When I say type vpol test is just a string for MATLAB. So it has to know, is it a variable in the workspace? If it is, it will look it up. If it doesn't find in the workspace, it says, is it a function? Where does it search for the function? In your own directory. First it checks in your own directory. There is a function there by that name. So it will type that. If it doesn't exist there, it will look into its path. Its path is huge. There are 10,000 functions or so it knows about. Okay, so it will search for those and then print that. In this particular case, it's going to print the function that I just wrote. Okay, so MATLAB knows about this function. Okay, one of the common problems that in the past people have encountered is you will use a name that already MATLAB has used before. Okay, then it can create a potential conflict. The conflict is resolved by the search path. So it will look in your path first, and then it will look in the path that it has. So if you want to use, for example, sine of 20, MATLAB knows what sine of 20 is because it has a function sine in its path. But if you also have a function called sine in your own library, it's going to use that. So it might give you the wrong value because your function might do something completely different. Okay, so conflict resolution of names is an important thing that you need to keep in mind. The next thing I want to do is test whether it executes. So it lists. Now I want to execute this. How do I execute it? I do vpol underscore test, and I give it the 2 input arguments that I have defined. Time is 0, and then I need to provide some initial guess. Okay, so 1 and 2, for example. So what did it print out? What are the numbers that it is printing out? F1 and F2. Okay, F1 and F2. Okay, so it takes those values of y1 and y2. y1 is 1, y2 is 2. It plugs them into those 2 functions and calculates F1 and F2 and returns that. Now, notice it returns F2 as a row vector. You may want to change that into a column vector because ODE-IVP expects a column vector. So that means we need to go back into the function and change this as f equals f transpose as the last line. Okay, and save that. Now, how do I use this function? Now I know how to calculate the function values. What are the interpretation for the function values? What does this number mean, 2 and minus 1, that I see here? You already said that is f1 and f2, but what else is it equal to? f1 is simply equal to f1 is simply equal to y2, that's correct. But what I'm looking for is something different. f1, you are absolutely right, is equal to y2, but f1 is also equal to dy1 dt. That is, f1 is the slope of the function y1 as a function of t. So at t equal to 0, 2 is the slope. Okay. Similarly, the second function gives you the slope for the second variable. It is the slope information that ODEs use to say, if this is the slope that tells me how fast y1 is changing, I can then predict what would be the y1 value at the next time step. We saw this already before. Okay, so that is why all ODE requires is the function name, because the function values represent the slopes, how fast the function is changing. Any questions? Okay. The next step is, how do I get a solution to this particular problem? Now, the function that I'm going to illustrate, as I said, is ODE-IVP. Okay. So an ODE-IVP requires the same input as ODE-45. And I will show you the difference between these two in terms of the performance. Okay, so here is the explanation. And the explanation simply says I need to define the name of the function, which I've written, the t-span, the time interval over which I want to integrate, and the initial condition. Okay, these are the three things I need to define. So I'll define t-span as equal to 0 to 3000. Did I say 0 to 3000 and enter 5? Sorry about that. So t-span, I want to integrate from 0 to 3000 seconds or 3000 units, whatever the time happens to be in that case. And y0 is given to me. Is given to me as what? As 2 and 0. Okay. If you look at here, the initial condition for y1 is 2, for y2 it's 0. Okay. Those conditions are initial conditions are given to me. Okay. So I need to take that and program it. So y0 is equal to 2, 0. Let me make this as a column vector. So to get the solution, all I need to do is t, y equals ODE-IVP. What do I do next? Very good. At vpol, the function name, vpol test, t-span, y0. That's all there is to it. So it's going to give me the solution. It's going to be a huge vector because I'm integrating over 5000. So let me put a semicolon and not print all of them out. Okay, it's done. In a fraction of a second, it's done. Okay, it has constructed the solution. Now I can plot. I can plot t, y. And what does it look like? It looks really strange, right? It's 0, and then it shoots up to minus 15,000 or 1,500, and then it comes back to 0, then shoots up to the other one. Both the graphs are on the same, both the curves are on the same graph. So when it looks like that, it's strange. You cannot make sense out of it. Okay. So now you need to pull that apart. You need to plot only y1 and then plot only y2. There is something very funny happening in this problem, and this is commonly happens in many reactor problems as well. That is, some of the variables are changing very rapidly over a very short period of time. And these kind of behavior are called stiff differential equations. That's why we need a different set of algorithms. So let me plot one at a time. Plot y. How would I plot y1 alone? Colon, comma, 1. What does that say? The colon says take all the rows, but comma and 1 says take the first column. Okay, so I'm plotting the first column in Y. What would be the structure of Y? Do you remember from the last class? It will be a matrix with, I don't know, maybe 5,000 lines or so, and 2 columns. Why do we let's print that out, okay? Or you can look here. There it is. Okay, it's 592 by 2. So here is my first column, and here is my second column. Okay, and I'm going to plot these two. So I plot Y colon comma, T comma Y colon comma 1. What do you see? Changes very slowly initially, and then boom, very sharp change. Okay, and then it changes slowly again, and sharp change, and it doesn't reach a steady state. If you do this from 5,000 to 50,000, you'll find this pattern repeats itself. This is called a cyclical behavior. If you look at the planetary motions, for example, if you write the equations of motion for the solar system, that's what the solution you will get, right? Because these are all going in circle forever. The planets are in orbit, right? So this kind of a behavior is very common with ordinary differential equations. You don't have a steady state, but you have a periodic state. Okay, this is for Y1, but look at the range of Y1. It goes from 2 to minus 2.5. So between plus 2 and minus 2, it oscillates between those two values. But if you do the same thing for Y2, oops, where is that? Y2 is the one that has this kind of a behavior. But the scale for this in the y-axis goes from minus 1500 to plus 1500. Okay, so the first time when I say plot Ty, it actually plotted y1 and y2. But y1 was squished because it was only going from 2 to 2, minus 2 to plus 2. Okay, so by separating them out, you are able to see. And y2 is basically like a switch. It remains at constant at certain time, just goes to minus 1500, then back to plus 0. And then it remains constant, and it goes to plus 1500 and back. Okay, so it is a very rapidly changing solution. Any questions? Okay, now I want to see the difference between ODE-IVP and ODE-IVP. How would ODE-IVP also work on this one? Okay, so let me just do naively, because I didn't know, suppose I didn't know anything about it. I know only about ODE-IVP. I'm going to use ODE-IVP to get the same solution using the same function. What am I doing? I'm just picking a poor algorithm that I don't know about. I hit return. Previously, with fraction of a second, I got the solution. Now I'm waiting and waiting and waiting. It says busy. MATLAB is busy calculating, and ODE-IVP is a very, very inefficient scheme, because the nature of the problem is it has periodic states, it has very rapid change. It's a stiff ordinary differential equation. It turns out that ODE-IVP is about 200 times slower than ODE-IVP. You might say, so what? Right? If it takes fraction of a second and that takes 2 minutes, I'm willing to wait 2 minutes. I don't need to know about ODE-IVP. I'm happy with ODE-IVP, right? It's perfectly fine. I'm still waiting, still not done, right? Now imagine this problem. You are getting introduced to mathematical modeling of physical processes, right? So weather prediction, they use very similar ideas, very similar algorithms. Instead of taking 1 day to predict the weather, if you have to wait 200 days to predict the weather would have come and gone, right? So you need a very fast, efficient algorithm. And that's where MATLAB and a lot of computational tools give you appropriate tools. So using the appropriate tools is very important to get the job done in a very efficient manner. Still not done. If you get into a loop like that, you're waiting in MATLAB, what do you do? How do you break it? How do you say, okay, I give up? But MATLAB doesn't give up. To break it, you do Control C. And it says, okay, it aborting whatever the calculation was doing and comes back to me. Okay. So to get an idea of how long it takes, I'm going to show you a simple test. And there's a function called, two functions called tick-tock. The tick-tock basically clocks the particular function. You can time how long it took to do a particular calculation. So let me change the t-span to 0 to 30. I never write 0, right? 0 to 30. Okay. So instead of going for 5,000 or 3,000, I'm just testing the speed. So I just want to see, okay, take a smaller step and see how fast you can do. Now the tick-tock functions work like this. You can actually ask for help, tick. Okay. So they tell you what the tick-tock function does. It's basically a tool for measuring the time taken by any particular algorithm. Okay. So the first one, the tick function, marks the current time. And taking that information, the talk function says, okay, how long it took, what is the elapsed time. So the way to use that would be, say, t1 equals tick, and then I type this execution, t comma y equals ODE-IVP vpol test comma t span comma y0. Okay, and then on the same line, I now call talk and pass the value of t1. So the way this is going to work is, first tick function is going to be called, which says what is the current time, 2 microseconds. It can record that in the variable t1. And then I make a call to ODE-IVP and say, go and integrate, see how long it takes. Once you have done the job, I'm going to call talk and say, since t1, how much time has elapsed? And it will print me that particular time. Elapsed time, as I said, is 0.017 seconds. That is really a very efficient scheme. Now I can do the same thing with, instead of 1.5, S45. Remember, now I'm going only 30 steps, right? And still it takes a long time. 6.14 seconds. So you can find the ratio. 6.14 divided by 0.017, 360 times. Okay. So there are tremendous differences in algorithms. So it is very important for you to pick the right algorithm. Okay. And the problem is, you don't know a priori beforehand, if I give you these two equations, that these two equations are going to be stiff, because I don't know the solution, right? So what you need to do is, that's a trial and error exploration. That's where the expertise comes over a period of time. You try 4, 5S and it takes forever, and you say, okay, I abort that. Is there anything else that I can use to speed up the same type of problem? Okay. Any questions? Yeah.
Is ODE-IVP always going to be faster?
Pardon me?
Is ODE-IVP always going to be faster than 4.5?
For certain classes of problems, like this kind of a problem where there is a very sharp change. Okay. When we see the algorithm later on, you'll understand what are the differences between 4.5 and 1.5S. Okay. 1.5S uses something called an implicit scheme, so it has the ability to anticipate change. Remember, when I told you how does it solve, it simply knows the slope, and from the slope it predicts what would be the value at the next time step. That's what ODE-IVP does, right? So imagine, that's a good question. So let me see whether I can plot that graph again. I should replot it with t-span of 300,000. The point I want to drive is, we talked about how ODE-IVP predicts by taking the slope. So if I am at a particular point, I calculate what the slope is and I predict what the next value will be. So if it changes slowly, the prediction based on the slope is going to be pretty good. But remember, if I am at the edge of this and I project the slope here, and I'm going to be predicting the solution to be here, but the solution has completely gone somewhere else. And ODE-IVP has the ability to anticipate such sharp changes because it uses something called an implicit method. It's the ability to anticipate. Whereas ODE-IVP does not have that ability. It just takes the current slope and predicts what the next value will be. And that's why when the next value is not accurate enough, ODE-IVP will keep on dividing the step size, taking smaller and smaller and smaller step size forever. And that's why it takes so much longer time. Okay. Yeah.
For this problem, is it just kind of a trial and error? You're gonna, you wouldn't know it was going to do this until you try to plot the graph.
Exactly. That's a problem. If I give you a brand new problem, and that's what research is about. Okay, the graduate students will encounter this kind of thing. They are studying something in the lab. They build a model, and they might have some idea from what they've observed in the lab. And once they have the model, they take it. The only thing they know is ODE-IVP, and it takes a long time. Then, okay, is there anything else you need to search at that stage? So, brand new problem, you don't know beforehand which one to choose. Okay, but in this course, what I would expect is I would accept whether in an exam, for example, I give you a set of ordinary differential equations. I don't expect you to know whether it is stiff or non-stiff, right? So if you tell me ODE-IVP, perfectly fine. I will give you full credit for that. ODE-IVP, perfectly fine as well. Okay, but you cannot say I will use fsolve to solve that particular problem. So I'm going to do that. Okay, so that to that level, I want you to be able to discriminate. Okay, any other questions? I'll show you the function that I wrote. We wrote it basically in class, but it's essentially the same thing, but with the cell structure and all that. Okay, so the first cell basically gets the solution using ODE-IVP. It's a script file. We did not in the class. We did it from the command line, but I'm putting all the same functions tspan y0 into that. And in the second one, I'm plotting y1. Okay, and here I'm illustrating a feature called subplot. Okay, so let's just go through that very quickly, and then we'll stop and move to the quiz. Okay, so let me execute the first one. There's nothing new in there. So I get the solution, go to the second one, execute that cell. Now I get a graph which is plotted on the top half of the page. Okay, if you want to save pages, if you want to compare two figures, this you can do by using something called a subplot. Subplot command, the first parameter says I'm going to have two plots in that page. You can put 4. That means I'm going to have 4 plots in that page. Okay, and then the second 2 parameters are matrix assignment. So I'm going to say the second plot 1 1 means it's on the top. Okay, and the second one would be 2 1, which would mean it'll be 1 2. Okay, that would mean it'll be below. Okay, so one below the other. And so I have plotted the subplot 1. Let me plot the second one. It's going to add to the same figure the y2. So I can see both y1 and y2 on the same graph. And I chose to plot the symbols in addition to the line, unlike in the previous one. From the symbols, what can I learn? I can learn how close these symbols are in the time axis. Okay, so when things are changing slowly, ODE-IVP is actually taking larger steps. Yeah. That's what the 0 puts O symbol. The minus sign says also draw a line. Okay, you can change that to plus if you want. There are certain symbols that are allowed. Plus, minus, triangles, squares. There are symbols for that you can put. Okay, so what you can see is, as in this region, what happens to the number of data points? They are very large. So it is taking extremely small step sizes because it is anticipating that it is going to change very rapidly. So it has this ability to change the step size automatically. Once it comes out of that, once again, it takes a larger step size in this region, and then a smaller step size again. Okay, so that's another feature that you can see by plotting the data in an appropriate fashion. Okay, and then the next plot is called the state space plot. We have also seen that in the cooling of a molten metal problem, where we are plotting y1 against y2. The previous plots are called time series plots. These are time series plots where We plot the state on the y-axis, y1 and y2 on the y-axis, time on the x-axis. So it's called a time series. But in the state space, you plot y1 against y2. Let me, before I show this, what do you expect? What would you expect the state space graph to look like? Put the thinking cap.
Just like y2.
Pardon me?
Just like y2, because y1 is so long.
Yeah, but you're plotting y1 on the x-axis and y2 on the y-axis. So y1 is going to change between -2 and +2. y2 is going to change between -1500 and +1500. Right? A steady state. What would a steady state look like in a state space diagram? We saw that already. A point, right? Once the trajectory goes and reaches a steady state. Once it's steady state, the values of y1 and y2 don't change, right? That's what a steady state is. So it's going to be a point in the state space. But this is not a steady state. It just oscillates. So if it were a pure sine wave oscillation, what would it look like in a state space? It's a beautiful circle. But in this case, it's not. So it looks like a closed loop. It goes forever in this path. As time goes, y1 and y2 keep repeating. That's what planetary trajectories are like. Closed orbits. Okay? So this is called a limit cycle. There is a name for this kind of a behavior. And as I said, one of the assignments, and I'm going to give you a third assignment, will be on a chemical reaction problem that exhibits all these behavior using ODE-15S or ODE-45. Any questions? So in every lecture, I'm kind of introducing a little bit of a new feature from MATLAB. And this one, how to use subplots, is an important thing that you learn to control, putting more plots on a single graph. Okay, and so it is important for you to study these piece of codes that you are using in the class. Let's stop there, and you get an extra 5 minutes. And let me distribute the